All right, hopefully this finds everybody healthy and happy today. Today we're going to do Chapter 13, an introduction to landform study. Again, we are using McKnight's Physical Geography, a landscape appreciation, published by Pearson. All right, and onward we go. Today we're going to go over the structure of the Earth, composition of the Earth, the study of the landform, some critical concepts, and scale and pattern. Again, this is part one, so we'll cover the first couple of topics today, and then we will have a continuation into part two for the rest of the chapter. So again, this is part one. Part two will follow. So the structure of Earth. Understand the Earth's structure based on a minute fraction of total depth, less than about 8 miles. So what does that mean? It means we've never been to the actual center of the Earth. How do we do that? How do we know what we got then? Well, we do it by geophysical means. We have sonar, we have magnetometers, we have seismic. We have all different types of tools we use, but when it comes down to it, much of what we know, we are simply inferring. Otherwise, we're making a hypothesis. This is what we think we have. Okay. There's 4 regions of the Earth's interior. If you look to the figure on the right, you will see that we have the crust, the mantle, the liquid outer core, and the solid inner core. So the crust. The crust goes down to a depth of 5 kilometers below the ocean to near 20 kilometers below land. You got to remember, ocean crust is more dense than continental crust. Continental crust kind of floats. So anyway, ocean crust is denser, and therefore you don't have to go nearly as deep below the ocean to get to the mantle. Between the crust and the mantle is the Moho discontinuity, and you do need to know this. You will probably see this again. It is a change of composition between the crust and the mantle. It's kind of like a plastic surface which allows the crust to slide around. So there's a kind of like an ecotone, if you would, between biomes. All right, except this allows the crust to slide around on top of the mantle. The mantle extends to a depth of about 2,900 kilometers or 1,800 miles. It is the largest of the 4 shells, makes up around 84% of the total volume and 67% of the total mass, so it's big and it's heavy. There's 3 sublayers. There's the lithosphere, the asthenosphere, and the rigid rocks of the lower mantle. The outer core, molten, extends to a depth of about 5,000 kilometers, and within it is the inner core, dense mass with a radius of about 1,450 kilometers, primarily made of iron and nickel or iron silicate. The 2 zones combined make up 15% of the Earth's volume, which isn't much, but look at that, 32% of the Earth's mass. It's small, but heavy. The inner core and outer core together, working together, control our magnetic field, okay? And our magnetic poles are not the same as the axial poles. You have to remember there's 3 norths. There's magnetic north, true north, and grid north. All right, and we're talking about magnetic north. And magnetic north changes. And we know that because of magnetometer readings on the Atlantic Rift, which is molten magma that pours out of the crust. And whenever they run a magnetometer down across these layers, they find that the north switches. You see, as long as something is liquid, the iron in it will orient itself to north and south, and then it will solidify and stay in that position. So we can sit there and take readings, and we can see that, oh, hey, north and south has switched. Well, about every 100,000 years or so, we have a reversal, a polar reversal, in which north becomes south and south becomes north. And again, we can tell this by the magnetometer readings. And we'll get into that again. You'll see a figure here in a little bit. Plate tectonics. Continental-sized plates slide along the asthenosphere. Remember, you got that Moho discontinuity in between the 2. Okay? And the continent, and this plate tectonics is known as continental drift. Now, we all know when we were back in school, we cut out the continents and you glued them all together and made Pangea. That just goes to show you how much the continents have moved around. And we've already talked about Australia in one of our other chapters. Australia was one of the first continents to separate off of Pangea, which is why they have so many marsupials, monotremes, and eucalyptus. That continent developed and evolved all by itself. Composition of the earth, minerals, naturally formed compounds, and elements of the earth. So mineral characteristics, you do need to know these. This makes a great ABCDE question. First of all, solid, found in nature, inorganic, specific chemical composition, and contains atoms that arrange in patterns to form crystals. As you see on the right, that's a crystal. Now, there are different elements in crystals, and we'll go over those here in a minute. Here's a fun fact about crystals. Crystals, if they are left alone within a certain atmosphere, habitat, whatever you want to call it, whether it's a cave or whatever, if they stay undisturbed and the atmosphere around them stays basically the same all the time, some of these crystals can grow to very, very, very large sizes. Humongous, in fact. So if you get a chance, Google up crystal caves, and you will see just how big some of these crystals can get. So, important crystal minerals. These are all pretty simple. I'm not going to ask you or test you on these. But silicates are, again, combined oxygen and silicone. Silicone. Oxides, combined oxygen. Okay? The oxides are also most common with iron, rust. Okay? Sulfides, sulfur, right? i.e. pyrite. Sulfates, again, sulfur and oxygen. Carbonates, carbon and oxygen. And carbonates have to do with limestone. We'll get into that later. We actually have a chapter on caves and cave development, so we will get into that later on. Halides, derived from the word salt, salty minerals, and your native elements such as gold and silver. Here is a table that just kind of tells you all the different ones that you can find out there. These are all minerals. All right, so rocks. Rocks are composed of many minerals. Fewer than 20 minerals make up 95% of the composition of crustal rocks. Now, over your figure, again, we know what most of these are, but an outcrop is simply exposed rock. Bedrock is buried, unexposed rock. Regolith is the broken up rock all the way up to the soil. And the word petrology, characteristics of different kinds of rocks. That depends on where you go to school at. Petrology at Oklahoma State University has to do with petroleum. If you want to study rocks at Oklahoma State University, you take a minerals class. Minerals and sedimentology, I believe it is. So anyway, depends on where you're at. But petrology doesn't necessarily mean the study of rocks at all institutions. All right, the three classes of rocks. There's the igneous rocks, fiery rocks, magma, lava, volcanoes. There are the sedimentary rocks, which is simply just that, sediment. It gets washed down the rivers, deposited into the ocean, and then it gets compacted and cemented. And then metamorphic rocks. Metamorphic can be either sedimentary or igneous that are then exposed to even more pressure and heat, which changes their overall composition. So, igneous rocks. Igneous rocks, fiery inception. Again, volcanoes. You need to know that magma is molten rock beneath the Earth's surface, and lava is when it flows onto the Earth's surface. So there is a difference between magma and lava. Magma within, lava without. Pyroclastics, those are those bombs. When you watch movies on volcanoes blowing, up LA or Tambor or any of these others, when it blows out the side of a mountain, these are the pyroclastics. These are what we call bombs. Okay, these are the big fiery rocks that just go for miles when they explode out and catch all kinds of things on fire. The classification of igneous rocks is based on mineral composition and texture. And texture is based on how rocks cool. We will get into that more here in a minute. So rocks, we have plutonic or intrusive, rocks that cool beneath the Earth's surface. Surrounding rocks insulate the magma intrusion, slowing the cooling, and therefore individual minerals in plutonic rocks can grow to large sizes, such as granite. If you'll look over to the right-hand side over there, you will see that is a typical piece of granite. It's got quartzite and feldspar, pink and white quartzite. And that is a typical volcanic or intrusive type of granite. Now, you ask yourself, where do we find these types of rocks? Well, how about the Rocky Mountains? But wait a minute, the lower Rocky Mountains don't have volcanoes. We will get into that. That is a question to answer later. One other thing to point out on these rocks is that the slow cooling allows crystals to get larger. It allows them more time to coalesce. So please remember that. The more time they've got to coalesce, the larger they're going to get. Then we have volcanic extrusive here, outside, okay, not intrusive, but extrusive, so outside, forming their surface, cool rapidly. Generally do not show individual mineral crystals, but can if the crystals are formed with shattered rock that was explosively ejected. Otherwise, one of those pyroclastic bombs. For instance, basalt, which is to your right. It looks like glass, okay? And a lot of Native Americans use basalt to make their points out of it. It's sharp whenever it's formed to make a point, or a knife, or anything else. But again, you don't see those large mineral crystals that you've seen on the previous slide. So let's go back for a second. If it'll let me, which it won't, never mind. Here we go. But as you can see, no large crystals. Okay, not like the granite. So anyway, looks more like glass. So you need to remember that slow cooling means larger mineral crystals. Fast cooling means it has glass. It doesn't allow those minerals time to coalesce. Here again, here we go. This is a good figure here. Here we go. We got our glass cooled fast, and we got our granite cooled slow. You can see the difference in the mineral crystals. And you don't need to know all these, but these are all associated with basically different types of volcanic, whether it's intrusive or extrusive.